Chapter 4, Section 27, Detecting Data Inconsistency Using Fuzzy Matching. In the previous section, we explored what data inconsistency is and how to detect the data inconsistency. For a small dataset, we can manually detect data inconsistency. However, for a large dataset, we need to automate the process of detection. The popular tools for automated detection are regular expression and fuzzy matching. The focus of this section is fuzzy matching, but for comparison, let's recap regular expression as a tool for detecting data inconsistency. Regular expression is a sequence of characters that specify text pattern. It is used to find, validate, and manipulate text that matches specific well-defined patterns. Regular expression matches patterns explicitly defined by the analyst. It operates with rules like specific characters, word boundaries, repetitions, and character ranges. We can use regular expression to detect exact patterns such as inconsistent formats and variations in spelling or case. Also, we can use to identify structural inconsistencies. Regular expression has some strength. First, it is highly precise. That is, it only detects what matches the defined pattern. Second, it is suitable for structured, rule-based inconsistencies. Besides, using regular expression, we can easily implement case-insensitive matching. However, regular expression has some limitations. First, it cannot detect variations that are not explicitly defined in the pattern. For example, typos like slice instead of cells will not be detected unless explicitly accounted for. Second, it requires expertise to write complex patterns. Now, let's focus on fuzzy matching. Fuzzy matching is a technique for finding approximate matches rather than exact ones. It measures the similarity between two strings and identifies matches based on a defined threshold. Fuzzy matching compares strings using algorithms like Levenshtein distance, which calculates the number of edits needed to transform one string into another. Matches are based on similarity scores, usually expressed as a percentage or a numerical value. So, fuzzy matching can find approximate matches when there are no predefined patterns. For deeper understanding of fuzzy matching, let's explore Levenshtein distance. Levenshtein distance is a metric used to measure the difference between two strings. It calculates the minimum number of single character edits required to transform one string into another. The allowed edits are insertion, deletion, and substitution. Substitution is replacing one character with another. Insertion is adding a character. Deletion is removing a character. For example, the Levenshtein distance between cells and slice is 2, because it consists of two substitutes, A with I and I with A. The Levenshtein distance is typically computed using a dynamic programming algorithm. Here's how it works step by step. First, create a matrix where rows represent characters of the first string plus an empty string, and columns represent characters of the second string plus an empty string. Second, initialize the first row and first column with incremental values, which represent the cost of deletions and insertions. Third, fill the matrix by comparing characters of the strings. For each cell ij in the matrix, fill the maximum of the following three values. Substitution cost. If the characters at the corresponding positions are the same, the substitution cost is 0 plus upper left cell. Otherwise, it is the upper left cell plus 1. Insert cost. The value from the cell above I minus 1, j plus 1. Delete cost. The value from the cell to the left, I, j minus 1 plus 1. Let's fill the cell 1, 1. For 1, 1, compare S from cells and S from slice. These are the same characters, so the substitution cost is the value from the upper left cell plus 0. It is 0 plus 0, so it is 0. The insert cost is the value from above cell plus 1. So the insert cost is 1 plus 1, which is 2. The delete cost is the value from the left cell plus 1. So the delete cost is 1 plus 1, which is 2. So the minimum of this cost is 0. So set the cell 1, 1 to 0. Let's move on to the cell 1, 2. For 1, 2 compares S from cells and L from slice. These are different characters, so the substitution cost is 1 plus 1, so it is 2. The insert cost is the value from above cell plus 1, so it is 3. The delete cost is the value from left cell plus 1, so it is 1. So the minimum of insertion, deletion, and substitution cost is 1. So set the cell 1, 2 to 1. By following the same steps for each subsequent cell, we can complete filling the matrix. The value at the bottom right corner of the matrix is the Levenshtein distance. Using the Levenshtein distance, we can quantify the similarity between the two strings. The similarity score between two strings can be calculated by this formula. A similarity score of 0% means the strings are completely different. A similarity score of 100% means the strings are identical. For cells and slice, the Levenshtein distance is 2, and the length of string 1 and string 2 are both 5. So the similarity score can be calculated in this way. It is 80%. Next, set the threshold. A threshold determines the minimum similarity score for a match to be considered acceptable. The threshold depends on the use case. High threshold, such as 90%, is useful when only exact or very close matches are acceptable. For example, high threshold is useful in matching customer names in a database to ensure precise identification. Low threshold, such as 70%, is useful when approximate matches are acceptable. For example, low threshold is useful when we want to find potential duplicates in messy datasets. Now, let's compute similarity score based on Levenshtein distance. First, import fuzz from Fuzzy Wuzzy. The Fuzzy Wuzzy library is used for string matching and comparison based on the Levenshtein distance. Here, fuzz is a module within Fuzzy Wuzzy that provides various methods for calculating similarity scores between strings. Next, define two strings, cells and slice. The goal is to measure how similar these two strings are. Next, compute the similarity score. The fuzz ratio function calculates the similarity between string 1 and string 2 as a percentage. This percentage is based on the Levenshtein distance, which measures the minimum number of single character edits needed to transform one string into the other. The similarity score is printed to the console. For these strings, the score is 80. Next, set a threshold for matching. The threshold value of 75 is set. This is the minimum score required to consider the strings as a match. Then, compare the score against the threshold using if and else. If the similarity score is greater than or equal to the threshold, the program prints a message indicating the strings are considered the match. Otherwise, it prints that the strings are not a match. In this example, the similarity score is 80, which is equal to the threshold. Therefore, the output is the strings cells and slice are considered the match. Let's go on to another example of Python implementation. This is an example of detecting potential inconsistencies using fuzzy matching. Specifically, this Python code uses the fuzzy-wuzzy library and pandas to identify potential inconsistencies in naming conventions within a dataset. First, from fuzzy-wuzzy, import fuzz and process. Fuzz provides functions for comparing two strings and calculating similarity scores. Process is used for string matching. Then, a data frame named data is created within a column called country, containing country names with inconsistent naming conventions. Next, define a function named find_inconsistencies to find potential inconsistencies based on similarity. This function is designed to identify pairs of strings in the specified column that have a similarity score above a given threshold. The default of the threshold is set to 80. First, create an empty list named inconsistencies to store the identified pairs of strings as elements. Next, by using a unique function, extract unique values from the specified column to avoid redundant comparisons. Next, use a nested loop to compare each pair of unique values. The condition I is smaller than j ensures that each pair is compared only once. The fuzz ratio function calculates the similarity score between value and other value. If the score is greater than or equal to the threshold, the pair is considered the potential inconsistency. Then, pairs with high similarity scores are appended to the inconsistencies list. Finally, the function returns a list of tuples, where each tuple contains two strings with high similarity. Finally, call the function. As defined, the first argument is the data frame, and the second argument is the column to analyze. The function outputs a list of potential inconsistencies. Let's summarize the strengths and the limitations of fuzzy matching. The first strength is that fuzzy matching can handle typos and human errors effectively. A second, it is flexible. That is, it does not require explicit pattern definitions. Third, it is suitable for unstructured or noisy data. Next, let's see limitations. First, it is less precise. Fuzzy matching may result in false positives when matches are too lenient. Second, it is computationally expensive for large datasets. Third, it requires tuning the similarity threshold to balance between false positives and false negatives. As a summary, Let me show you this table, which compares regular expressions and fuzzy matching in terms of their approach, use cases, strength, limitations, and example scenarios. As for matching approach, regular expressions is rule-based, relying on explicit patterns. On the other hand, fuzzy matching is similarity-based, enabling approximate matches. The strength of regular expressions are high precision and predictable results, while fuzzy matching is effective in addressing typos and human errors. As to limitations, regular expression is limited to predefined patterns, less flexible. On the other hand, fuzzy matching is less precise, with a higher risk of false positives. About use cases, regular expressions are suitable for structured patterns, formats, and rules. So, it can be used for validating email formats, detecting case differences. Fuzzy matching can handle typos, misspellings, and unstructured data. So, fuzzy matching is useful in identifying similar terms such as matching, slice, and cells. Thank you for watching. Please thumbs up and subscribe to my channel.